Hi, I'm Vincent DeLucio, and I'll be covering Chapter 3, which is Polynomial and Rational Functions. So in 3.1, we have polynomial functions and models. So to start, we'll be identifying polynomials and their degree and graphing polynomials using transformations. So looking at this polynomial right here, we'll be finding the degree, and to do so, you look at the x plus 1 to the fourth. So you know that the leading term will have an x to the fourth. So knowing that, the degree is always the highest exponent. Now, looking at transformations, we look at all the transformations done to the parent graph of x to the fourth. So here we can find a vertical shift of 3 units up. So vert shift 3 up. And then looking, and we know that it's a vertical shift because it's on the outside of the equation. Now looking in the equation, we can see an x plus 1. And when looking at inside the equation, it's a horizontal shift, and they're always the opposite. So it's a hori shift 1 to the left and not to the right. And then finally, we see this 3 here, and because it is on the outside, it's not connected to the x, we know that it is, and it's connected to the polynomial, we know it's a vertical stretch of 3. So now looking at the graph, we can see this green is the parent graph, and the blue is this graph shifted left 1 unit, up 3 units, and it is smaller because of the vertical stretch. So now going on, we will be identifying the real zeros of a polynomial function and their multiplicity. So here, same thing, we're doing f of x equals -7 times x minus 4 times x plus 6 quantity squared. So looking at this, we can see our zeros are going to be 4 and -6. They're always the opposite of what they are in here. So we have 4 and -6. However, because our -6 is the formula, because it's grouped with the x and is raised to the second power, we know that it has a multiplicity of 2. So now moving on to the next section, 3.2, the real zeros of a polynomial function. We'll be using the remainder and factor theorems, Descartes' rule of signs, as well as the rational zeros theorem for this equation. So the remainder and factor theorem, first you want to find if this given x minus 2 can be a factor of f of x. So to do that, use the remainder theorem by plugging f of 2. And if f of 2 does not equal 0, and which in this case it doesn't, it equals 2, then x minus 2 is not a factor of this equation, which it's not. So x minus 2 is not a factor. So then after that, we have Descartes' rule of signs. So for this, we plug in a negative x in all of our x spots. So then we have here, and after we do that, we'll get negative 4x cubed minus 7x squared plus 3x plus 4. And then we can find out how many, so now we can find how many positive and negative zeros we can have. So we know we have a max of 3 because of the degree. So now our max positives, we look at the original equation and see that there is 1, 2 sign changes. So we have 2 or 0 positive zeros. And for negative, we look at this equation with the negative x and find that there's only a single sign change. So there can only be a possible of 1 negative 0. So now we'll be using the rational zeros theorem. To do so, you need to find the factors of a sub 0 and a sub 3, which are the final and the leading terms. So a sub 0 equals 4, and a sub 3 equals 4 as well. So then we change that to p, which is a sub 0, and we factor 4 out, so you get plus or minus 1, plus or minus 2, and plus or minus 4. And then you have q, which is a sub 3, which is the same factors. And finally, you do p over q, which gives you plus or minus 1 plus or minus 2 plus or minus 4 plus or minus 1 over 2, and also plus or minus 1 over 4. So these are all of your possible rational zeros for this given equation. Moving on, we have find the real zeros of a polynomial function and solving a polynomial function. So we will be doing that for this equation right here, or this polynomial function, which is f of x equals 2x raised to the third minus 11x squared plus 10x plus 8. So again, we'll be doing the rational root theorem. And we'll do a sub 0 equals 8 and a sub 3 equals 2. So again, p this time will equal, that's an equal sign, plus or minus 1 plus or minus 2 plus or minus 4 and plus or minus 8 this time. And q this time is only plus or minus 1 and plus or minus 2, giving us p over q of plus or minus 1 plus or minus 2 plus or minus 4 plus or minus 8, as well as plus or minus 1 over 2. So then we begin to start plugging in our possible zeros to try to find one that gives us a remainder of 0. So in this case, if we plug in f of 2, we get a remainder of 0. So we know that 2 will be one of the zeros to this equation. So after this, we use synthetic division to get our depressed equation. So here we have our synthetic division set up. And we'll have a 2 here, excuse me. We'll have a 4 here and negative 7 here. And then we have a negative 14 here, a negative 4 here, a negative 8 here, and a 0 here. Now to get these ones, so 2 is always going to be 2 here, and then you multiply this to get this number, and then you add these two together to get this new one down here. So now our depressed equation is equals x minus 2 times x 2x squared minus 7x minus 4. So now we can factor this equation out, so we do not have to use any more synthetic division. And this would factor out to, let's see, x minus 2 to 2x plus 1 and x minus 4. So knowing this, we can get our real zeros of negative 1 over 2, 2, and 4 for this equation. This leads us to the intermediate value theorem. So the intermediate value theorem is if f of a and f of b are different signs, then at least one zero is between a and b. So to use this, we'll be using this equation, and we'll be using the set of -3 and 0. So first we find f of -3. So we plug in -3 to all these x's. So then we get 10 times 3 to the 4th minus, or excuse me, -3. So 10 times -3 to the 4th minus 4 times -3 squared plus 5 times -3 minus 1. And when all that is computed, we get f of -3 equals 758. Next, we'll find f of 0, which is pretty easy because anything times 0 is 0. So f of 0 will equal -1. And because these two have different signs, we know that there is at least one real zero between -3 and 0. Next up, we have section 3.3, which is complex zeros and the fundamental theorem of algebra. So to start, we'll use the conjugate pair theorem and find specified zeros. with this given information. So we know there's a degree of 4, so there's 4 zeros, and we're given 2 of them. So using the conjugate pair theorem, we can find that negative I is one of the zeros, and then negative 8 minus I is the other zero. So then, to find the polynomial, you'll do f of x equals a times x minus I times x plus I times x minus 8 plus I times x minus negative 8 minus I. So then you would multiply all those out to get the equation f of x equals a times x to the 4th plus 16x cubed plus 66x squared plus 16x plus 65 as your polynomial. Next for this section, we find complex zeros of a polynomial function with this given function. So to do so, we have to use Descartes' rule of signs again. So we know that there's a max of 4 zeros. And looking at the equation, we know that because there's a sign shift here, there's a max of 1 positive. And if we plug in a negative x for this, you'll still get x to the 4th. So we know that there's also 1 possible negative. Now we use the rational zeros theorem. So you get a of 0 equals 1 and a of 4 equals 1. So then p equals plus or minus 1, q equals plus or minus 1, and p over q equals plus or minus 1. So now we try to find a 0 using the remainder theorem. So if we plug in f of 1, we get 0. So then we use synthetic division. Set it up. We get 1s here. And then we get our new depressed equation of f of x equals x minus 1 times x cubed plus x squared plus x plus 1. And then we try f of negative 1, which does also equal 0. So then we would do synthetic division again, and you'd get your new formula of x minus 1 times x plus 1 times x squared plus 1. So finally, to find the last 2 zeros, we would do x squared plus 1 equals 0, which is x squared equals negative 1, and then x equals plus or minus the square root of 1, which is plus or minus I. So your zeros for this equation would be negative 1, negative I, 1, and I. Next, we have 3.4, properties of rational functions, and 3.5, the graph of rational functions. So in example 1, we have the equation r of x equals 10x plus 10 over 7x plus 14. So for this equation, we'll be finding the domain, a vertical asymptote, and a horizontal asymptote. So to find the domain, we set the denominator equal to 0. So you have 7x plus 14 cannot equal 0. So then you have 7x cannot equal negative 14. And then finally, you have x cannot equal negative 2. So for the finding a vertical asymptote is the same thing, except you set the denominator to equal to 0. So then you find that your vertical asymptote is x equals 2. And for your horizontal asymptote, because the degree of the numerator and the degree of the denominator are the same, you know that there will be a horizontal asymptote. So you get 10x, and then you cancel out the x's, so you get y equals 10 over 7 for your asymptote. So here's the graph of this function, and we know after finding our asymptotes that they are here and here. So this is what the graph with asymptotes would look like for this specific function. And now again, we are doing the same thing, except this time we will have an oblique asymptote. And we know this because the degree of the numerator is higher than the degree of the denominator. So same thing for here to find the domain, or x plus, or x, yeah, x minus 1 cannot equal 0. So x cannot equal 1. So our vertical asymptote would be x equals 1. And for our oblique asymptote, this time we have to use division. So we'll do the denominator, or I'm sorry, the numerator, x squared. You have to make sure you add in your 0x, because otherwise you will mess up your equation. So you have the numerator divided by the denominator. So then you divide it out, then you get negative 3x squared plus 3x. So then, that's a plus sign, you'll get 3x minus 2, or excuse me, plus 2. And then you, again, 3 to get rid of the negative, the 3x here. Then there's a 3 here. Then you get negative 1. So your oblique asymptote is y equals negative x. So then you come over here, and here's our graph for this equation. Let me get all this off of here. So here's our graph for our previous polynomial, and using what we found, we know that our vertical asymptote is here at x equals negative 1, and our oblique asymptote is here at x equals, or y equals negative x, and comes down like this. Now, while graphs cannot go through vertical asymptotes, it is okay for graphs to go through horizontal and oblique asymptotes. So finally, to end this section, we have 3.6, polynomials and rational inequalities. So to start, we'll solve a polynomial inequality by using this graph. So first, we're going to be solving for when f of x is greater than 0. So that would be this section here, as well as this section right here, from 2 onward. So knowing this, we have negative 1 to 0, union 2 to infinity. So now for our other equation, or our other inequality we have to solve is f of x is less than 0. So that would be this section past negative 1, and then this section from 0 to 2. So that would be negative infinity, comma, negative 1, bracket. And it's a bracket because they're inclusive and it's less than or equal to 0. And then also here, this is a bracket, 0, 2, and another bracket, because all of this is inclusive because it can be equal to 0. And then finally, we have solve rational inequalities. So we're going to solve if r of x is greater than 0 when r of x equals 2x plus 4 divided by x minus 1. So this is the inequality we're given, and when solved, we know that our asymptotes will be x equals negative 1, so, or excuse me, 1. So here, sorry for the crooked line, and then y equals 2, so here. That should be broken up a little bit, but I digress. So then we're solving for r of x greater than or equal to 0. So again, it will be this section onward from when it hits at negative 1, and then this section onward. So we have negative infinity comma, -1, and that's inclusive, union, but because it's on an asymptote, it cannot equal 1. So it's 1, comma, infinity. And then that leads us to the end of the chapter. I hope it was helpful information, and thank you.